Hey, here again with Yehuda. Today we're going to look at re-implementing ActiveSupport String blank method in Rust.
Cool. So basically, me and Godfrey were working on this a couple weeks ago, and I was trying to teach him Rust, and we realized that there was already a good C extension that was pretty scoped in size, pretty small, that made sense to re-implement in Rust, and we could do and actually run the ActiveSupport task and run benchmarks, and we can run benchmarks against the C extension and all that. So I'll just show you that C extension real quick. So that's on Sam Saffron Fast Blank. And what you can see is he has C extension. He's already written some benchmarks. When I worked with Godfrey, we actually imported his benchmarks, but I don't have them today. And if you look at Fast Blank, what you'll see is that there's a C function here that's pretty long. But it's kind of like what you would expect out of C, right? A lot of hard to understand stuff you have to sort of learn. And probably if you were doing this for the first time, you would not have figured it out. So it's very unlikely that you would have re-implemented this in C because I personally probably would not have ever done this because it would have taken me a long time to figure out how to write. And you can see at the bottom, the most important thing to understand about C extensions in Ruby is that when you have a C extension called fastBlank, you create a global function called init_fastBlank, and when you require the compiled C file, it will automatically execute that function, and that gives it an opportunity to define a bunch of methods. So that's basically the bridge between Ruby and C code. And the most important thing to understand about Rust is that Rust is, from the perspective of Ruby, Rust is just another C program. We'll see exactly how to do that, but that makes it very easy to interface with C because Ruby already knows how to interface with C. So as long as we can take Rust, make a compiled output that looks like C and give it to Ruby, we're going to be good. So let's look at how to do that. So I'm going to start. So first of all, I have cloned the project that I worked on with Godfrey. And what you can see here is that there's a basic structure. And if you're familiar with Bundler, you hopefully will find cargo.toml and cargo.alloc at least slightly familiar. So let me show you what those things look like. So the cargo.toml, it's a toml file, in large part because perhaps the only way you can actually get away with having a gem file being written in the native language is for it to be Ruby. I don't think there's a plausible, other languages are just too verbose. And I've come to like the toml structure. So you have a package section that tells you your packages, then you say what your name is. In this case, I have disabled document tests, although it's a cool feature that often basically you always want to use. And then the important thing on line 9 here, and this is going to be true for the general strategy that I'm outlining today, is that the output of compilation normally is a library, like a library or an executable that is meant to be, the executable is meant to be executed and the library is meant to be consumed by other Rust code. And in this case, what we are saying is we want to make a library that's meant to be consumed by C code, and we want that library to be statically linked. We want it to be to include everything, all the dependencies inside of it. So what line 9 is basically saying is I want you to compile the Rust code into something that looks like a C program, basically, C library. And then finally, because this program requires C, we have a dependency on libc. Libc is basically just a library that allows you to interface with C. In this case, the reason that we are using it in this crate is because we need a way to transport strings across the boundary reliably, and it happens that I have written the code in this package, in this crate, but in principle that should have been a crate that you imported. So instead of importing libc, you would have imported buff, and for sure should release that. And I'll show you in a minute what that, or a little bit later what that does. But I think for the purposes of this screencast, it's not so important what exactly that does. It's just a way of safely taking a string from Rust and giving it to Ruby and vice versa. Just because the implementation of strings inside of Rust is pretty opaque. It's unstable. So you have to do a little bit of work to get the raw pointers out and put them in a space that Ruby can understand. But that's, again, pretty straightforward. So let's start by just looking at the Rust file. You can see here, this line over here, libc equals 0110. That line is actually corresponding to this line, extern create libc. And what that's basically saying is, I want you to actually make libc available in this file. So it's like maybe like require in other programming languages. I also want to point out that there's this thing called cargo.lock that's in all of your projects in Cargo, and it works effectively the same way as Bundler. It takes all the dependencies and it pins them to the exact place where you should get the dependency from, right? So what that means is that you can say something pretty loose in your dependencies, and you get a lockdown version of exactly all the registry and everything like that in Cargo. Now we've imported libc. We're importing the buff type that I defined in the other file, and then the most important thing is what starts on line 9. So first of all, we say no mangle, and what no mangle just means is that normally when you compile a Rust program, it does not expose the symbols in a predictable way to the program, to the C program. Because that, if it did, then you would have collisions between your Rust program and every other program in the process. But sometimes you really do want C to have access to your program, right? And so, And so what you want to do is you want to basically start by saying it's no mangle. The second thing is on line 10, you want to say that this function is actually a C function. And saying it's a C function doesn't actually mean that it's not a regular Rust function. It's callable like a regular Rust function. It just means that Rust should not try to perform any optimizations on the calling convention that it might perform if Rust was calling other Rust code, right? So it basically says make sure that this function is actually callable from C in the normal C kind of way. So, and then we give it a function, tr for turbo rails, stir is blank. We take a buffer, and then what we do a few more things. So the first thing that we do is, let me just bring up the buffer type. So the buffer type is a little involved, but the most important thing, there's two important things about it. First of all, the buffer type has a wrap function on it, which takes a string and gives you back a buffer. And then it has another function which has a slice, an as_slice method, which takes a buffer and gives you back a string wrapped in a result in case it might fail. You can see here that it's possible that you got a null back from the other side and you explode. Although I think you could probably get away with relying more heavily on the C side to not do bad things. But the current version of this code explodes if you give null instead of segfaulting. So what we do is we basically say, okay, this code is assuming that the C side gave it a buffer, and we'll see soon in the C code how you achieve that. And then we say, also the definition of buffer is that it's a pointer, a length, and this thing that doesn't appear in the actual representation. It just basically allows it to understand the lifetime interactions between C and Rust in this case.
This buffer type, this is only temporarily in this project.
Yes.
You're going to extract it out
yes,
to a
exactly.
cargo package.
Yeah, so you shouldn't this is definitely like a more complicated Rusting, largely because it's encapsulating interactions between C and Rust and trying to make those interactions safe so that you could use them reliably. Let me put back the cargo.toml here. The way that you would use this type in any project that was this talking between Ruby and Rust would just be to take a Rust buffer type and use the API. You would not have to think about the crazy stuff that I just showed you on the other screen. So the first thing that you do is you're going to get a buffer from C, and again, we'll see in a minute how C goes about giving you a buffer. We unwrap, which just means panic. Don't segfault, but panic if there's a null. But again, I think the C side should not give you nulls, and probably the buffer type doesn't have to worry about that. And then the next thing that we do is, okay, now we have a regular Rust slice. And if we look at, let's go to the Rust documentation.
A slice is a type of string in
Yes.
in Rust.
So maybe I should rewind for a second and explain basically there's two kinds of strings in Rust. Let me just bring up what I was thinking about, and then I will say what I'm talking about. So first of all, there's a thing called stir in Rust, which is the thing we're talking about. And that's the thing that types. I'm looking for the thing that has cars on it. So basically in Rust, there are two types of strings. There is a string that is basically part of another string. So think about in Ruby when you have a big string and you split it over commas or something. There's no actual reason why it's necessary for you to create new string objects, put them somewhere on the heap, maybe duplicate them, have to track embeddings, right? So Ruby tries to do some optimizations to sharing, but fundamentally it's hard to reason about when those optimizations actually apply and when they don't. In Rust, if you do a split, so let's look for a split over. So there is a split API. That is the type that you get back. So you can call a split takes a pattern, which could be a lot of different things, but one of the patterns are implemented for other slices for characters, right? So you can say split over a single character, split over a string, split over an array of characters, things like that. But in practice, what you would actually do is you would say some string. Here we have a slice dot split, and then you would say something like comma, and you get back an iterator.
Mm-hmm.
And so in this case, what you're actually getting back when you call split is you're getting back an iterator over things that are windows back into the original string. So we start off with a regular string, and then we get back a window instead.
Right.
And so the idea is that, and this is actually really interesting. It's something that you may not intuit initially, but a large percentage of the time, probably like 90% or more, you're actually not operating on strings on something that needs to be duplicated. You're actually operating on a piece of another string somewhere.
Right.
And so in Rust, most of the time, you're working with slices, which are just windows into some other string. Occasionally, you work with capital S string, and that's when you need to make a string and put it somewhere.
Okay.
So, and interestingly, when you if you type, so you can see here, there's some places where I type some strings. When you type a string by default, what you're actually getting is a string that is embedded in the program. So it's actually, the string never has to be heap allocated. It's actually just in the program binary. And so you might sometimes see people type something like foo.toString. And you might be like, what? That doesn't make any sense. I thought it already was a string.
Yeah.
And the reason is that the first string is just a window into your binary, which is actually very nice that you can do that. It means that you don't have to allocate things if they're always the same in your entire program.
Yeah.
But sometimes you need to take that and put it somewhere that requires a heap allocated string that might want to mutate it or might want to do something else. And in those rare cases, you need to type toString.
Right. If I use the same string characters in double quotes multiple times in my application, is Rust clever enough to realize that actually they're the same thing?
So I don't know, but I think it probably does.
Right.
So what we have here importantly is the buffer type gives you back a slice, not a string. And a slice, basically, it's a slice because the Ruby side has the actual string, and the Ruby, we don't need to duplicate the string just to work with it, just to find out if it's blank. That's silly, right? So the Ruby side is going to give us effectively a window into the Ruby string, and now the Rust side can just keep operating on it. And the important thing here is that because Rust has this division between strings which you own and slices which you borrowed and have access to a window of, we can be very efficient, and we can also be sure that we're not gonna, if we keep calling other methods on slice, we can be sure that we're not gonna somehow screw up and start like corrupting somebody else's memory, right? Because the slice type here, the as slice, if I actually do want to go back and show it, even though it's a little scary, as slice actually returns this thing, which is, so if you look at this original thing, right, we get a buffer from C, and we're returning back a slice that has a lifetime attached to it, which basically means you cannot allow it to escape. So the important thing about this is that if you try to say like thread spawn, which makes a new thread, and then inside of your thread spawn you try to get access to B, it's going to be like, no, you are not allowed to do that. And the reason for that is that the Ruby side just called you. It's expecting you to return right away. If you start taking the Ruby data and putting it into a thread, that's going to explode, right? So basically this type, even though as a user of the type, you don't have to worry about the exact lifetime management, the fact that it actually is taking the Ruby pointer and converting it into a managed lifetime for you helps you avoid making mistakes that would corrupt the data.
Yeah. Are we able to modify this string data as Ruby sees it within the scope that we're in here at the moment?
So you would have, me and Godfrey talked about that. You would for sure want to call Ruby functions to do it. And I think what you would probably want, if you want to actually deal with mutable Ruby things, which I think probably ultimately people I don't think people ultimately will want it if we continue down this path. What you want to do is you want to make a wrapper around the Ruby string that actually knows how to call into the Ruby methods, but gives you some You basically don't want to necessarily have every single thing you ever do call into the Ruby methods, because then you end up doing very inefficient things. But sometimes if you actually, effectively mutating is like, has consistency issues, right? So if you're reading and you know that you're the only one reading at a given time, basically there's a GIL, you're looking at a consistent view of the world, then it's pretty easy to read and be like, seems good. Ruby gives you some guarantees. But if you're writing, basically, you want to go through Ruby's functions because it's the thing that maintains internal consistency of the objects. And you could, Rust has things like overloading the indexing operator and things like that could make it pretty ergonomic to work with these things in a nice way.
Okay.
Like you basically wrap the calls back into the Ruby functions. And actually remind me to show later like how you would actually declare that you have access to the Ruby functions in the Rust program.
Right. Okay.
So anyway, that's basically what this phantom data scary thing is. It's basically just saying, so this runtime, this lifetime doesn't actually come from Rust. The Rust compiler doesn't understand it, but I want to make a lifetime right now because I want to make sure that people don't make mistakes.
Okay.
And so from here on out, this S basically is going to be only allowed to be used directly inside of this function, not in another thread somewhere or something like that, and not in another struct that gets passed to another thread, etc. So again, you don't have to worry about any of that. It's the nice thing about lifetimes in Rust is that a lot of the time someone else has thought about how to describe what is the ownership story or the borrowing story, and then you just get compile time errors if you make mistakes, right? So the first thing we did was get a slice, and again, this is just a Rust representation of the pointer that's inside, the pointer and length that's inside of the Ruby object. And then the next thing that we do is we call s.cars, and I was getting to the point where I could show what that does. And so what cars does is it's basically it operates on slices, strings, and it returns an iterator of cars, right? And I can talk a little bit about what iterators are, but the basic way to understand iterators is that they're the fundamental way that you loop over things in Rust. So one thing you could do with an iterator is you could say for car in s.cars, and then you can work with the cars here. And that basically automatically is going to call the next function for you and exit the loop when you're done, things like that. So you can do that. But more usually in Rust, since Rust has a lot of like functional programming flavor, quite a lot like Ruby, right? So in Ruby, it's very unidiomatic to use for in loops because there's usually a better way. You can use an each if you really need to, but there's like map and things like that, and it's actually, a thing I really like about Ruby is that Ruby embraced the idea of that functional programming pattern of if you want to loop over something, there's often a better way than just looping. Mm-hmm. There's often something better that you're trying to express. And so in Rust, if you have an iterator, there's a bunch of methods on all iterators, which is like count, last, nth, zip, map, filter, right? All this stuff that you would expect. The type signatures are scary, but you don't need to worry about it. That's kind of a story of Rust right now, is that in 2015, in September 2015, the person writing abstractions often has to do a lot of work to express what's going on, but the person using abstractions has an easy time with it. And there's a lot of work, like a ton of work going on to reduce the burden of writing abstractions in the first place in all kinds of ways. And I expect that there will come a point where it's pretty ergonomic to write a lot of these kinds of abstractions. But today, there's certain points where when you're writing sufficiently generic code, so iterators are generic, right? When the implementation of all, I'll actually show you the implementation of all. So the implementation of all is actually implemented once for literally every iterator. And you can specialize it, but this is an implementation that can work for every iterator. And the consequence of that is that at some point you're getting to a fairly generic place, and there are limits to how much more generic you can get. So in this case specifically, the consequence of that is that the all method returns, actually the all method is a good example of some place where it's not that big of a deal because it just returns a Boolean. But for example, like the map function, what you would ideally like is just to say the map function returns some kind of iterator, right? And you don't care what kind of iterator it is. It's not really part of the type signature. You would like to be able to express that. But we have basically gotten to a point here where things are sufficiently generic where we cannot, in Rust today, actually express that. And so you end up creating a concrete type called map, which is another iterator and implements all the iterator protocol. Mm-hmm. So if you're just like chaining, everything works great. You don't notice. Yeah. But the consequence of that is that the person writing the whole iterator library, which is an extremely generic library, had to write a bunch of types that in principle, that get leaked into the public interface that in principle you would not want to leak.
Right. What's the way out of that? What's the...
So one of the ways out, there's basically two ways out that that are actually really similar to each other. The simplest way out, if I grab this function definition. So here's the current description of this, and it's a hairy thing. And you could imagine there's effectively a plan to let you say, I'll leave the F in here, but allow you to say self of impl iterator of, what is the type here? I think there's like you're iterating over whatever. It's like iterator of whatever the iterator that you're inside of is iterating over. No, of course not. It's it's B. It's the return value, right? So what's happening here is that there's a function that's returning a B. So of course the map function is giving you an iterator of that same thing, right? So this already, and you still have to say where f of fn. This is pretty crazy in my opinion. So you still have to say this, but I think like this is a lot simpler. It actually makes the signature longer, but it actually doesn't leak the exact type that you're doing. So that's one improvement. There's an improvement that I want, which is basically to go back. So this thing, fn mute at the end here, is basically just saying, so in Rust, every closure is actually implementing one of the function traits. And usually in programming languages, that have types and closures, there's a way to express the closures in a way that looks syntactically similar to the closure syntax itself. And in Rust right now, you have to actually say this somewhat long thing. Actually, there is a slightly better version of this, which is you would be able to say with that impl thing, you'd be able to say impl fn mute of self item. So it's like pretty annoying that you have to move these things out. Right, so I think this is like a little more, this is already a little more readable, right? It's saying it's a self, takes a function that implements a mutable function of self.item that returns a B, and then that returns an iterator of B. I think that's already a better signature, but I would like us to figure out syntax that would let you write something like, I'm actually transcribing this totally incorrectly, but I would like you to be able to write something that looks like the closure syntax that you would have called. And I think that gets you to a place that's like pretty, like the last one here is like getting pretty reasonable. Actually, we could always have removed these Fs now that we hid their types, right? I think we're starting to get to a pretty reasonable place here, but there's work to be done to make that work. So that's one vector, is just like making it possible to express things that you could already express better. And when I say you can already express, some of these things are actually not expressible. When I say you could already express, you could express them using hacks, like where you're returning a special type. There's another vector, which again is quite often equivalent, which is called HKT, or higher kind of types. And basically the problem that higher kind of types is trying to solve is that sometimes, and this is when I said sometimes you get too generic and then you're stuck. Sometimes the thing that you're actually trying to express is not this class operates on vectors of T. Sometimes you want to express this type operates on vectors, and somewhere later somewhere else will give me T, and I'm going to combine them to get the type of vector of T when someone actually tells me what T is later, right? So basically, you normally think of when you have generics, you normally think of it's a generic over a concrete type. But higher kinds of types is the idea that you want to be generic over like a quote-unquote type constructor, which is even more generic. And if you know Haskell, you realize that this is really where Haskell starts falling off the complexity cliff, because people, when you get really generic tools, people use them to implement really generic, hard, impenetrable abstractions that are very, very general. And I think there's a desire in Rust to make sure that mostly people don't use the tools to do crazy stuff, and figuring out how to message that is important. But those are basically the two tools. I think the point is that I just said a lot of very complicated type system theory that probably I got some of it wrong. But really, if the impl thing, for example, the explanation might sound complicated, but if you just had it, it would actually be pretty easy to understand what is happening, right? You're basically saying, I'm not returning a specific thing, I'm returning a thing that implements this thing. The fact that that unpacks into a pretty long method signature that looks like what we were looking at is not that important. So anyway, I think the TLDR of all of that, if somebody like just got lost and wants to come back to understanding how to embed Rust in Ruby, is that today writing an abstraction in Rust is sometimes hairy, especially writing abstractions that take closures or abstractions that deal with lifetimes or really generic abstractions are hairy. And basically the Rust team knows that, and we have a strong desire to improve the ergonomics of writing, of basically dealing with really generic code. I think the good news is that there's actually, if you think about, like, for example, in Ruby, metaprogramming is a complicated topic that a lot of people don't understand that well, but a few people understand it, and they write abstractions that work well, and using like the router in Rails or something doesn't actually require you to understand metaprogramming. And I think roughly there's going to be a similar split in Rust where writing code that's like so generic that you need to understand type constructors is like not really going to be a thing that it's going to be the equivalent of metaprogramming in Ruby, right? Someone has to understand it so they can write the most generic kinds of abstractions. And in Rust, those things are really fast. But you as a user can get away with just using the API that was given to you. And today, unfortunately, today when someone does that, it results in types that look like this.
Yep.
And I hope later when someone does it, it will result in types that look more comprehensible. It doesn't really massively affect the amount of work that an abstraction author has to write, except that when an abstraction author is himself using abstractions, it composes better, right? Okay, so getting back to the code that we're actually looking at.
Right.
So we have a slice. We got a cars. That's just an iterator. Every iterator has all, so we loop over it. Takes a C, and then a car. So it yields a car into the block, and let's look at what car does. Yeah, the documentation is actually pretty hard to find what you are looking for. I want the car type. It really, here we go. Actually, it does say it. Okay. And so there's a is whitespace on it, right? And the nice thing about is whitespace is that it actually already is defined in terms of Unicode. So I didn't say this before, but all Rust strings, so there's Rust arrays and slices of arrays, which are just whatever type. And it's pretty common to have a slice of U8, which is just a slice of bytes, which is raw binary, which is like the equivalent of a binary string in Ruby. But strings are always UTF-8 in Rust. So if we're operating on strings and we have cars that are from strings, we know for sure that everything is Unicode.
Yeah.
And so is whitespace already operates on Unicode. And if you go back and look at Sam's original thing, what you'll see is a lot of what he's doing here is just like dealing with Unicode code points, which ideally one does not have to worry about.
Yeah.
So we have is whitespace, and what we're going to do is so now we have s.cars gives us back an iterator that all is a method on all iterators that takes a closure, yields a car into the closure. Now we call sc.is whitespace, and that does the same thing that like the Ruby all method does.
Yeah.
Now, one thing that you have to get used to, initially almost everybody thinks this is terrible, but it ends up being, I think, a pretty good syntactic hack, is that if the last statement in your function has a semicolon, that means that the return value is empty, void. And if the last statement in your function does not have a semicolon, it means that return this thing. And that basically matches up to the return value. So if I actually add a semicolon to this thing and try to build the project, it's going to say like, hey, you are expected, you have a return value of bool, but not all control paths return a value. And actually, if I wonder what's going to happen if I run this. Yeah, so you get a description that's basically like, what are you doing? You should try to do this other thing, right?
Yeah.
So it's not, I think because of the fact that you're always saying what you return, this particular thing is not as bad as it might be in like Ruby, where I think you would just mess it up all the time and be very confused, right? Here, if you put a semicolon where one doesn't belong, you actually get a type error, which is good. But what that basically means is that you can, there's a visual distinction between I'm returning something, I'm not returning something. And I think initially people usually are like, find the visual distinction confusing, but before long it's in second nature, and it's actually a very terse way to say the thing that you were saying.
What's the I mean, what's the reason for doing that rather than introducing like a return?
So there is a return, right? Okay. But you use Ruby, you know it's nice to not have to type it.
Right. Okay.
Right. Also, I think the way to think about the semicolon is that it implicitly, so if you don't have a return here, it's actually implicitly saying return this thing, which is unit.
Yeah.
And if you put a semicolon in, it's like implicitly doing this, I think. I think that's the way to think about it. It's not a magic operator, it's a separator.
Right.
And if you have a separator, there's the invisible statement is the unit statement, just like it's the invisible statement when you don't have any return value at all.
That's nice. I have a way to visualize it now. That'll stamp me forever, I think.
Yeah, I mean, I think once you get used to it, it's fine. It's basically just every language has syntactic tricks that make it easier to understand common things, and whether or not your function is returning something is actually a really common question, and having a nice terse way to express it is nice. Yeah. It's just that people are so used to semicolons meaning a very specific thing. I think Jose Valim was like, semicolons with semantics seems crazy. It should be like a Lexer thing. And it's definitely a thing that you're used to being a certain way, but it's a thing you learn, and it's great. I think. Does
this hint at a certain philosophy within Rust?
Say more.
Well, so Ruby, for example, has multiple ways of doing things, and that permeates right throughout the language design, and also influences people who build libraries on top of Ruby. So is there like a set of those sort of rules or guiding principles that makes these kind of decisions easy to make?
So I actually think that's kind of there's like an irony to that, because Ruby is also the host of Rails, which is a very one way to do it thing. And I think there's a tension between those things. I think Rust is interesting in the sense that it is a systems programming language, so it's designed to do a lot of things, but it tries hard to find good paths for the thing, for like trying to do something. So I guess my philosophy on the one way to do it thing in general is you want there to be one good way to do it, but you don't want that to be the only way to do it. And I think defaults are really good. Just like it's well known that opting in versus opting out is like a totally different question for humans. So defaults really make it easier to keep going down the happy path, and you can be tired and you still do the right thing. And I think Rust definitely cares a lot about making the normal idiomatic way that you write code one way, and the way that the Rust team thinks is the right way. But it also is pretty careful to make sure that there's other ways to do things if the default way doesn't give you what you want. Because again, at some point you're basically writing C, and at that point you need really fine-grained control. Cool. So this is a good example of that, actually. Like, this line is what the Rust team would like you to write.
Yeah.
So we have this line, works great. I should probably actually return a bool again. And I've written some tests here. So this is sort of the idiomatic way of writing inline tests. So Rust Cargo supports both inline tests and integration tests. Integration tests are basically meant to be testing your public API. So it's basically like, here's the API that my library is supposed to use. And integration tests run as if they were a separate library, a separate crate that can't actually see the inside of your crate at all, has to work through the public API, and the compiler actually enforces that, right? So if you didn't say that something was, so here I said this is pub, here I did not say that this is pub, so an external crate cannot actually see this module, but it can see this. And that's great. I think you definitely want to write tests like that, but it is also the case that when you're writing an individual module, you often have tests that are just, you might be writing a complicated algorithm, and you just want to make sure that the little thing that you're writing actually works. And this is not a thing I had done a lot before Rust, but I actually really like the fact that in Rust, things that are about effectively private behavior actually stay with the private code, right? Instead of, in Rust there's not a lot of choices because the actual the visibility requires you to put it here. But I think that's good. I think it's great that, there's another thing I should point out, I realized, which is that this thing on top here says pound bang feature test. When you say bang after a pound in Rust, that means this applies to the enclosing thing. So in this case, I'm inside of a module. I actually can't, there's no syntax for the module that I'm inside of. So I need to actually say that I'm adding the feature test to the enclosing module, not the next statement. Whereas these things, no mangle, CFG test, this bench annotation apply to the immediately following thing. So I think that's once you get used to it, it's pretty clear. So okay, so the next thing is we want to write some tests. And so the idiomatic thing to do is to make a module called test. So that's just a module, a nested module like any other, although usually nested modules would be nested in the file system. So an example of that here, I have a module called buff, right? And what that's saying is unlike this one on line 17, there's no curlies. And what that's saying is basically there is a module in the file system. It's relative to me right here. Basically treat it like it was this module over here. So that it basically effectively is like typing mod buff and then putting all this stuff inside of here, right? Okay, so let's go back. So we have a bunch of tests, and now interestingly, tests don't actually have access to their enclosing scope. They're a little isolated. So the first thing I do is I include basically all the stuff from my super, although in this case, it probably would have been fine for me to just include specifically super tr stir is blank, but it's pretty idiomatic inside of tests to just say like, give me all the stuff from the outside. I'm just testing private stuff right now. This is fine, but if I started having 5 or 6 things, it would get annoying fast. Yep. Second of all, I include the benchmarking library. I'm using the one that's inside of unstable Rust for the purpose of this, but probably in the real world, you would use a crate that did benchmarking for you. And finally, I pull in my buff library. When you say use, it's important to note that use always refers to if you just start without any prefixes, it always refers to the top of the crate, right? So when I say use buff : buff, I'm basically saying go back to the top and go find buff and then go get the buff type from inside of it. But you can also say use super : which basically says go up 1 level, or you could say use self : foo, which is basically says go down 1 level, right? So you basically can describe different things. Typically, this is the thing that you want because typically when you're importing things, you're importing things from utility libraries, and they're probably like pretty close to the top of your crate. But all 3 forms are common and for various reasons. Okay, so the first thing that I did here was for the purpose of the test, I'm not actually talking to C. So I'm just going to take a function. It occurs to me that this is pointless. I should make sure anything compiles. Great. So the first thing that I do is I make a new function called isBlank, and it's just the function that's going to actually run the isBlank function. It takes a Rust string, it wraps that Rust string into a buffer, and then it calls the underlying thing, right? So in C, I would get the buffer from C, but in Rust, I'm actually just wrapping it manually and passing it. And then I wrote 4 things here. The first thing I wrote was test. So in Rust, if you just want to run some tests, you just put the test annotation before your function, and then you can use assertions. And then I just wrote 3 benches. So I wrote one that benchmarks the empty string, and you can just say b.iter and takes a closure. And for the same reason that this code on top is fast, you don't have to worry about the closure introducing costs like in Ruby or something. And then I test it with a string, and I test it with some white space. So I basically now have a test suite that has 3 benchmarks that I could perhaps use for regressions, and a set of tests that I basically cribbed from Rails.
Perhaps you could show what a failing test looks like.
Yes. So first sure, I can.
Or any test, I guess.
Yeah. So I can. We can do this. Yeah. I was gonna. So far I've just been showing you a lot of code, but actually the thing that's cool about Cargo in general is the Cargo workflow. So I'm just going to remove the target directory here. And so that means I'm starting as if I had just cloned the repo. And if I then run cargo build, it basically says compiling libc, which is compiling my dependency, and then compiling turbo rails. The output there is basically just a consequence. It's saying, hey, you're compiling a static library. Make sure all that other stuff is actually there in the program that you embedded in. But note that if I run cargo build again, nothing happens. And if I if I save this file and run cargo build again, it doesn't recompile libc, right? So basically cargo is smart enough to only recompile things that have actually changed. Also, there's a cache in cargo. So let me show you what happens if I run cargo update. So cargo update is like bundle update, and you can see it says updating the registry. But actually, after it updated the registry, it's a Git repo of the registry. Mm-hmm. After it updated the registry, it noticed that actually everything was still the same, So it didn't have to do any work, right? So basically it's pretty equivalent to bundler. I learned a lot writing bundler, and I think there's better things about how the way the cargo system works. So cargo build is like the main way. I would say cargo build is probably my main loop when I'm writing code. So if I go in and let's say I make a mistake, right, and I remove the return. Okay, I'm making some white space errors here. If I remove the return and run cargo build again, it's going to say like, hey, you failed. You're supposed to return a boolean and you returned a you're supposed to return a unit and you returned a boolean instead. Please fix. Right, so I usually just run that a lot while I'm programming, effectively as a type check. And there's actually been some discussion in the Rust project about making the specific type check loops faster. So this is actually not just type checking, but actually compiling and sending to LLVM. But for the type check loop, you really only care about type checking. And so there's probably going to be like a cargo check or something that just runs, just compiles and does type checking and gets out. But for now, cargo build is fine. There's also cargo build -- release, which produces a release build. If you, do I have tree? I don't know why I don't have tree. I love tree. Ubuntu is crazy. What is even happening right now? Wow. That is, I have no idea what just, anyway. So if we run tree, you'll see that there's basically two targets. There's the debug and release target, and they look pretty similar. You can see that cargo is automatically compiling libc for us, and that's like where the cache actually lives. If I had any examples, it would compile those when I ran my tests, and then it also produced the output, which is turborails.a, right? So there's many possible things that could happen, but this is a pretty simple output. So cargo build -- release does that. Now we can run cargo test. What cargo test does, I should probably actually fix that type error. I guess I have two type errors now. They cancel each other out. So we run cargo test, boom, we got a test error. It's basically like you have a problem. That is actually not an amazing failure message because I did not write an amazing failure message. Hilarious. It should say like expected blah not to be or to be blank. Okay, that's a lot better. The format macro is basically just it takes formatting strings and the thing that you're formatting. In this case, it's basically saying the colon question mark is like saying inspect in Ruby, so it's saying I want you to inspect this thing, and that's why the output looks like a string and not like empty, which is what an empty string would normally be printed as, right? So we have a test, but we should probably make it pass, right? So note, by the way, the test is actually passing. So that's pretty nice, right? We're basically running is blank on various things. Again, these tests were copied from ActiveSupport, and it's passing, which is great. So so far so good. And the next thing that we can do is we can run our benchmarks, and that's also just cargo bench. You don't have to remember anything special about release mode. Obviously, cargo bench always runs your benchmarks in release mode, right? So we run cargo bench, it compiles us, and you will notice that it's 0 nanoseconds per iteration. That is actually not a bug. That it really is taking 0 nanoseconds per iteration to find out that an empty string is empty, which is actually not all that surprising, right? An empty string is empty is a pretty easy question. And if you think about what must be happening conceptually here, right? S.cars returns an iterator that has nothing in it, so all is very easy, right? But of course, if you go back, if you look at S.cars, right? So let's look at the cars function. So there's going to be implementation. I actually really like exploring code on GitHub, by the way. Not searching, but exploring is great. Yeah, here we go. Whoa. So you can see that cars is actually not doing like simple thing, right? It's creating a new struct cars, which has an iterator in it. It's calling self.as bytes and then converting the bytes into an iterator, right? So and if you look at iter, if you look at core, it's going to be slice. Let's look at that fn iter. So a lot of code is going on in here, right? And then the all method we saw before actually loops over things. So you could imagine that this is going to be slow, but actually in the case where there's nothing in it, the consequence of all that compiled code is that there's not anything to do, or effectively nothing to do.
Right, and what is the mechanism that changes all of that, what could be expensive, to almost nothing?
Yeah, so you should definitely watch my talk if it's on video. But the TLDR of this is that when you say s.cars.all, Rust actually knows. So first of all, in Rust, and this is definitely something you should watch my talk to get a better sense of.
What talk is that?
It's the talk at Full Stack Fest, which hopefully will be on video soon.
Okay.
So at Full Stack Fest, the whole talk was about this exact topic, why it's fast. In Rust, when you make a new thing, the default is stack allocated. And the important thing to understand about stack allocated is that stack allocated eliminates effectively all the usual costs related to allocation. So it's not like actually free, but it's as close to free as you could imagine, and it's so far away from the cost of heap allocation that it may as well be free. So when you, the important thing is that the compiler basically allocates space for the thing that you're stack allocating at compile time, and it gets removed simply by the process of going up and down the stack, right? So the natural way that you move around your program naturally destroys things that need to be destroyed without any specific bookkeeping related to that thing, right? So when you say s.cars, we saw before that it makes a cars struct with an iterator inside of it. The first thing to understand is that all that stuff is just stack allocated. This program, this function, knows that s.cars is going to require an iterator, and so it leaves space in the compiled representation for an iterator of the right size. And then the second way that all that works is that even though s.cars.all is a generic thing, so in a regular programming language that had polymorphism, you might think that it's hard to know exactly what's going to be called. And again, it's not just that it's polymorphic, right? The function all is actually defined to work on any iterator, right? So you could imagine that the only good way, in language with the interfaces, usually once you start using interfaces, you have to wait until runtime to figure out exactly where you're going. But the way Rust happens to implement polymorphism, which is actually just a copy of what Haskell does with some improvements related to unique things about Rust, is that when you use polymorphism, it's not saying, go figure out at runtime what to do. It's actually saying, go figure out compile time what to do. So so imagine that you have a function called like read line, and it takes any reader. Okay. Let me show a better version of the syntax. This doesn't exist, but this is like proposed syntax that I think will exist. So it's like reader, and it takes anything that implements read, and it returns, let's say, a string. And let's imagine that reader has like read until /n. This is not a real thing, but let's imagine that this was a thing, and then you could do like toString. So this is not a real, basically none of this is real, but it's like illustrative, I think. So the point is that so this function basically is calling read until, which is a thing that exists hypothetically on all readers that ever existed. And again, in traditional polymorphic situations, you would just compile that to be like dynamically look up read until at runtime and go call it. But the way Rust works is it says every single time someone calls readline with an actual concrete implementation of read, make a special version of that function. And so you're going to make a version of the function that effectively looks like fn readline for memory reader, and then that's going to say reader of memory reader, and it returns a string, right? And then that's going to be, it's going to have the same body, but this body is actually pointing at an exact location. So this function, which actually is the thing that gets used in the real world, knows exactly where you're going. And the reason that this is really important is that inlining is a gatekeeper optimization.
Yeah.
Once you can inline something, it's actually possible to see the whole thing that the program is doing and perform additional optimizations. And LLVM in particular really relies on being able to see what's going on. And if you start inserting dynamic dispatching into the compile step, then the exact kinds of things that make this very fast end up failing, right? So let me delete this stuff, but basically what ends up happening is that s.cars is returning a stack allocated iterator, so that actual process of making that iterator is small, and objects, structs in Rust are not like big complicated objects. When you make a struct with a couple fields in it, like this struct over here, this is literally just like enough physical space in memory to hold those two things. It's not like doing crazy stuff, right?
Yep.
Like in Ruby, if you make an object, it's creating an R struct with stuff in it. And that's usually, many languages have object representations that are involved. But in Rust, what you see is what you get. It's making space for those two pointers. A pointer and a use size, actually, in this case. So a stack allocates the iterator, and then the all function, it knows the exact all function for the cars iterator, right? So let's go back actually to the cars iterator. So here's string cars. So I think it actually does not implement a special version of all, right? But this is actually the point. Sorry, I'm just trying to make sure. I want to be accurate. So here's the iterator. Something must say like impl iterator for cars. Here we go. Yeah, so you can see that iterator, implementation of iterator is literally just implementing what should happen next, which is go get the next code point, and then if there is a next code point, give me, it says mem transmute, which basically says here, strings are guaranteed to be UTF-8, so we can be sure that the bytes that we actually got here are UTF-8. And then size hint is basically just a way of saying what the actual size of the thing is, which is a way of telling the compiler internally, like, hey, you can be sure that you can't be sure. You can assume that it's this size. There's been some proposals for a trusted size hint or something where you're like, you can actually be sure. And then maybe we could like communicate that to LLVM. So the cars thing has not actually implemented all, right? Remember, all was implemented on iterator. So iterator is a trait, which means it can have default methods, and all is just implemented as a default method on iterators, right? So let's go back and look at that again. And what it's doing is it's getting the self by reference, looping over all the things that are in it. If there's no, if it's false, if calls the callback with the thing that it just got. If the callback returns false, it returns false. Otherwise, it keeps going until the end. It returns true. And note that so by ref. So by ref is actually just a thing that takes mutable self and returns. It's an adapter basically. So you don't have to really know. It's basically the way to think about what's happening here in FN all is basically it's saying loop over all the things in myself, and note that it is also able to use the looping syntax here, even though that is probably not like the quote unquote most efficient from a high level language perspective. So it's looping over the thing. If it calls the callback, if the callback is false, it returns false. Otherwise, it ends up returning true, right? Oh, by the way, here's the return syntax you were asking for.
Right.
So it's like Ruby basically. You can avoid.
What I find fascinating about this is that we're at several times we're hitting the metal, and we're still able to fit the whole picture in our heads.
Yep.
If we were to do the same in Ruby and follow it all the way down to the metal, right, we certainly couldn't do that. And this probably explains the huge difference in speed between these two methods.
Yeah, well, I mean, certainly a big part of this is that a lot of we're following it, but actually Rust has a philosophy of zero-cost abstractions, and this for in thing is actually a zero-cost abstraction. This callback, I'm going to explain in a second, is zero-cost abstraction. So I think it's actually nice that it's not just that there's less layers, which is nice, but it's also that the layers are, if you try to do the same thing in C, you would basically not have good abstraction tools. Right. So you see it calls the callback here in the all function, and the point that I was making is that this all function also takes a generic callback, and it's running on a generic iterator, But when we actually create that call in the real world, we create a specialized version of this function just for the exact situation that we're actually in, which is that we're actually iterating over cars.
Right.
So actually, I should have kept the cars. Up. Okay, cars. So remember that cars has a next function, right? So basically what's happening here is that this loop is invoking the next function over and over and over again, and it waits until it gets a none back, which is going to happen when next code point event. So next code point, if you look at it, fn next code point. So basically next code point returns either a U32, a 32-bit integer, or it returns nothing, right? It returns a none, which is the null type in Rust. And note that in Rust, you are allowed to say that something is nullable, but we have seen a lot of functions already that aren't nullable, and that's great. It's great that if something doesn't say it's nullable, you don't have to worry about null. So next code point actually does a bunch of stuff. I actually love this line. Note performance sensitive to the exact formulation below. But you basically, this is the metal, what you're looking at here, right? This is the actual low level. And so basically what this thing does is it's basically saying it returns either sum of U32, this thing. It either returns sum of U32 if it finds a code point, or it returns none. And the way you interact with an option type in Rust is if you have some option, you can say option.map of the actual inner value, and then you can do something with the inner value, and that basically will basically propagate the none. So if the original thing was none, the new value of option.map is none. Otherwise it's not. So basically, otherwise it's the value that you return from the closure. That's basically just sugar for if you have an option, you can say if it's sum of value, then I want to do something. Otherwise, if it's none, I want to do something. That's the basic syntax, right? And the map function, which I can actually bring up, it seems okay. So the map function also takes a function, right? This fn once basically says the function only runs one time, and that basically just means that you can move things into the function. If it ran multiple times and you moved something into it, you would have many aliases and you'd have memory issues. So this is basically just saying, hey Rust, I promise I'm only going to call this one time. The compiler makes sure that that's actually true, and that gives you more power basically. But you can see that it's matching over the option type, and then it says, okay, if it's a sum type, actually call the callback and return a new sum type. Otherwise, if it's none, just return none. And that is a thing that this next function here is using, right? So, and again, this is something that like in Ruby would just be like ludicrous because you're like introducing closures and callbacks and whatever. And in Rust, literally like this thing just becomes this thing. So there's really no reason not to do it. If it's convenient, just do it. Seems fine.
Yep.
So every time we're getting the next code point, right? We're looping over, we take the iterator, we get the next code point, and then we say, okay, if there actually is something in there, return a character, yield the character into the block, and then we just convert that into the output. So the input, I think, for next code point, the next code point returns an option of U32, which is a 32-bit number, right, an unsigned 32-bit number, and the next function actually expects to get back a character. We say, okay, we actually know that 32-bit numbers that we get back from here are valid characters because of the fact that strings are guaranteed UTF-8. So it's fine in our case internally to say that it's a character. And that's actually the rule about unsafe in general, is that you're only supposed to use unsafe if you have a reason to believe that the whole surface of your API has a guarantee that makes it actually safe. You're not supposed to use unsafe. The way to think about unsafe is it may have been called trusted or trust, right? It's saying Rust doesn't know that this is safe. The raw operation is unsafe. Yeah. But I know for some reason I've written my API to know that it's safe. And generally speaking, that's the whole point of safety, right? Is that if you write a good API, your API is not going to actually segfault, but it just forces you to think about why that's true. In this case, it's because if you actually look at the API for the new function, am I not in string? I am. So the way strings get created basically is when you make a new string, you say, give me a string from UTF-8. The safe versions of that actually check to see if they're UTF-8 and will actually either panic or give you back an error if it's not a UTF-8. And then there are unsafe ways of saying, I promise it's UTF-8. And that's like for cases where you know you got it from another C library that already promises that it's UTF-8. But the idea is that the internals of this code know for sure that it actually is UTF-8, and therefore they can be sure that they can promise, they can do things like that unsafe transmute and be fine, right? So, okay, so we're like following the rabbit hole here a little bit. But basically what happened is we had this all function, and the all function is asking for the next code point, and then it's calling the closure that we gave it with the code point, right? So now we call that closure. So we were looking at next here, but here we're back in the iterator, right? So we're calling the callback. We're calling the callback with a character. And this closure actually is a thing that implements, if you look at the all function, it's a closure that implements fn mute. And let me bring up the fn mute definition real quick. So fn mute is the trait that when you write a closure, Rust internally converts it into a struct and a trait. And it's a trait that has the implements call mute on it. It takes itself, the thing that represents the closure, as a mutable thing, and it passes the arguments that you gave it as arguments. So one way to intuit what I am talking about here is that if you write this closure, one way to transform that closure is to write struct closure. And you can see that this closure actually closes over C, right? So you need a slot for the C. So you basically have like car of, like probably we can, I'll call it character of car, right? And in this case, you don't have to, you don't know that it's a character necessarily, but the type inferencer figures it out, which is also a philosophical thing about Rust, is that generally speaking, we like you to not have to write types inside of functions, but we think it's good to write types at the function boundaries so that when you're looking at a function, you know what to expect. Internally, it's like cognitively cheaper to not have to worry about it, and we found that that's a good trade-off. So basically, when you have a closure, you're basically making a closure with the character in it in this case, right? And what the call mute function, and of course some code, right? So there's some code. So there's basically going to be like fn call and call mute in this case, right? And it takes. I'll write the version as if you were going to write the struct inline. So it takes the closure as closure, right? And it takes args as, in this case, yeah, I guess. So actually, it has no. I'm wrong. In this case, the closure doesn't have any. It doesn't have any fields, right? It doesn't need any. It doesn't close over anything. Actually, all the things that it looks at are the things that get passed into it. So it's just a simple struct.
Okay.
And actually, in Rust, simple structs that have no fields are free. They're the compiler. They don't actually allocate memory or anything like that, but they're markers for the type system. So the type system says, oh, that you better actually have that real thing. So we have a function called call mute, takes the closure, and then it takes arguments. And the arguments in this case, what are arguments? It's just a generic, right? So in this case, it's like, I actually don't know what it would expand into off the top of my head, but you could imagine that it's like a array of things, right? It's an array of, in this case, car. And what it basically does with that is it goes args 0 dot is white space, and it returns a boolean, right? So you could imagine basically creating this transformation, and actually what you would do is you would say impl fn mute. I don't actually want to write I don't want to spend time writing the actual generic here. Fn call mute of self. So you want to implement it for a closure, right? Self args car returns a boolean, and then you go arg0 dot is white space, right? So that you could, like this something like this transformation is actually happening, And basically, so now we have a type with that implements fnmute. And if we go back and look at what all is doing, it says, give me a type that implements fnmute. Great, so now we have one. And if we basically pass that to all, although I don't know if it's actually possible to implement these traits today yourself in stable Rust. But you could imagine that this is what's happening, and you can pass it, and it's great. However, this is extremely annoying to write. It's kind of like what Java makes you do.
Yep.
It's much nicer to have closure syntax and inference and all this stuff. So basically what ends up happening is that this syntax actually gets transformed into a struct that has fields for all the closed over variables. In this case, we have none of them, plus an implementation of the appropriate trait that you're trying to call.
So there's a series of inline operations, and ultimately this thing becomes a chunk of code that is just extremely fast for your exact
So in this case, the cool thing about this, right, is that what we actually have here is a function that is totally static. And so you, like, effectively you could just, so I'm just going to, for the sake of argument, for simplicity, just say this. This is actually not how it works, because of the fact that there's no what would be called variadic generics. But I actually don't know precisely how this would be implemented. I guess you could make, you could. I think you could just make it anything. You could probably just make it anything. Although it implements fnmute, maybe fnmute tells us more. It does not. So I think basically you could just say fnmute of car. I think this is roughly correct, right? But then if you could say something like fnmute of car, that's a tuple syntax, and then you could do this. That would probably work also, although I'm not sure. The point is, so we have, I will call this args, right? So we have this implementation. So basically what happens is that this arg that is white space is the only interesting thing that's happening here, right? So, it's not the only interesting thing that we maybe discover later at some point. The compiler actually can see, once it does the transformation from this thing to this thing, that it's literally the only interesting thing happening here. So it can just take this arg that is white space, and just, when it makes the all function, it can just remove fx and replace it with arg that is white space, or in this case, x that is white space, right? And that process keeps repeating, right? So that was just a little window into how static analysis can work. And the cool thing about it is that, the static analysis is pretty rigorous, quite rigorous, right? Like when you do the transformation, it's like, oh, that is quite obvious. But you didn't have to do that. You wrote some syntax that Rust carefully crafted to make sure that you could always be converted into something like this.
Right.
Right.
And line 21 there just looks like a line of Ruby.
Exactly. So basically, we just went through all the crazy stuff that Rust is doing to make it nice. But ultimately, what ends up happening is that we have this thing, and it is effectively the way that it effectively ends up working, right? If we unroll everything, is that it's looping over the thing, right? So that ends up calling. So we're in cars. That was next. That calls next, right? And next called. Where's next code point? So next calls next code point, but that's also, we know exactly what that's doing, right? So next code point also. So basically, we're just going to inline this, or maybe it's too big, so you don't inline it, although this looks bigger than the machine code for it actually would look like, right? So we're basically calling at this point, we're basically calling next code point a bunch of times. This map is basically just a null check. So internally, if the question is like, is it, so let's go back to the option thing, right? So this is basically just a match statement, right? So it's just like, is this a sum or none? And internally, things that only have one. So if you look at the definition of option, it's an enum. If you look at the definition of option, there's two variants of it. There's the none option and the sum option. And there's a special case basically in Rust where if you have exactly two variants and only one of them have anything in it, it can be represented internally as a nullable pointer, right? So a nullable pointer is what we're actually representing here in C. And so it just is a nullable pointer. It's just that we have safety to prevent us as programmers from messing it up, right? So the map function here is effectively saying, is this null? If so, don't do anything. Otherwise, call the callback. And internally, it doesn't require any extra wrapping because remember, we have a pointer that is either null or not null. So we just take the thing that's inside of here and put that into the pointer, right? And so basically what's going to happen is it's going to say, let me unroll that actually into code. It'll be easier. we actually at some point should probably get to the how to do it in Ruby, right? Sorry, let me. I'm pasting. Okay, so basically this is effectively saying. Let next equals next code point. Set no paste. Set no paste. Let next equals next code point of the iterator, right? And then like if next equals null, such JavaScript, or if x does not equal null, right? Then transmute, which is also a free operation, so it actually doesn't do anything. So it's basically just like done. That's it. So basically, there's some code here that's dealing with like internal safety properties. But okay, we have an next code point, a nullable pointer. We can now move on with our life, right? And then the next thing that happens, it's like looping. It's basically saying if there's no f of x, so it's basically calling that callback, which was basically saying, is it white space, right? So let's find our is white space. Tell me I have it. No. Okay. I'm almost done here, but I think this is actually somewhat illustrative, so it seems good. I remember I had to get it from the code. Is white space. It's on car. That's why I got lost. Okay, so it's actually the problem is this doesn't have the source attached to it. Okay, one moment. So I think it's going to be in libcore. So libcore is like the core part of Rust. Libcore car. Is white space here? It is not. Okay, I don't actually know where it is, as it turns out. But is white space, if you recall, is basically just effectively that C thing, right? So I was wanting to walk through why that ends up being true, but I cannot. I feel like we looked at it before. Let me try one more time. So this is saying test is white space, which leads me to believe that is white space is actually in here. So you can see it's pretty exhaustively tested, but that is not actually where it is. We can probably post-process some of this out. It's like amazing that I cannot find this. This is less, what? So like, why is it finding this file if is white space is not in it? Because it's in comments. Seems annoying. I feel like this is blowing my mind. It may be that it's somehow built in because it's like primitive type. That must be what it is. No, I have found, no, that's in librussy. Although this is probably fine. Yeah, so, okay, great. This is, I don't know if this is the exact code that's being used, but it is probably acceptable for this purposes. So basically it's a function called isWhitespace, and you can see it's using high-level pattern matching syntax. Then it basically says, is it an empty character? So it's actually kind of nice that it's like, so there's range syntax, right? So if you go back to Sam's example, there was like this big case statement. if you go here to the Rust version, it is actually expressing the same thing, right? And then we basically say, okay, if the answer is, if it's in this range, then it's white space. If C is greater than, so pattern matching syntax also lets you embed just whatever checks you want. Usually you can say it declaratively, but sometimes checks are needed. In that case, it returns property white space of C, which I actually don't know where that's coming from and don't really feel like figuring it out. It's a Unicode. It's basically asking, so basically it's saying, okay, there's some characters that we know are white space because they're ASCII. Otherwise, ask Unicode if it's white space. Otherwise, return false. I suspect white space here we go. So it's basically internally it has a piece of range table, etc. Right? So basically, there's code internally. It's going to eventually end up getting unpacked. But fundamentally, when it says, okay, I have the next code point, so let me rewind back to the point I was trying to make originally, right? So the first thing it's doing is it's looping over the characters. So that's basically this code because we said, okay, it's an option, but that's basically a nullable pointer, so we're good. The next thing it does is call the callback, but we actually see that the callback is just calling is white space, and is white space is just running this code. Is white space is just running this code, and this also effectively ends up getting compiled down into this thing, right? It looks like what Sam did is he hard-coded Unicode characters that he knew were blank, and it looks like Rust actually wants to check. But if it's within the range that we know is normal, it's fast. Otherwise, it's probably pretty fast. And so what basically ends up happening is that now we're like, okay, run this function, which is basically like effectively this thing, right? And then it basically, it's going to run some stuff, and then if it ends up in this branch, it's going to end up being true. So that ends up being exactly equivalent to what we were doing before, right? So we can basically, I'll do a little inlining. I'll basically do this, right? So we're basically ending up doing something analogous to this, right? Then we're like, so remember, so we're looping, right? So then it's like, okay, if the callback returns false, which is going to be these cases, then we're going to say, okay, we're done. So the answer is going to be return false. This is like some kind of pseudocode I'm writing here. It's not real code. So this would be something like function whole operation. Right, which operates. Yeah, I'm writing so much not real code that it's like the syntax highlighter is like, what are you even doing? So it takes an iterator or something like this, right? So basically, when we're done inlining, it's actually just writing the code that we would have wanted to write. And even next code point might get inlined depending on heuristics, and pieces of that might get inlined, right? So we start by writing this high-level thing that basically looks like Ruby, but because of the fact that all the intermediate abstractions are careful about saying what they're actually doing, the full thing is very easy to be converted into the correct code, right? So the consequence of this whole thing, first of all, is that if we just, I'll leave this around for a second. Let me remove this. So remember that when we benchmarked, we were surprised to learn, by the way, this is a VM. I'm running inside a VM, so it's like actually quite fast. We were surprised to learn that benchmarking the empty string was 0 nanoseconds, but we should not be that surprised anymore about that, right? Because basically what happens is that we're iterating over something. Let me see if I can find it. We're iterating over something that's empty, right? So the next function, so let's find the fn next for cars if we can. So the next function calls next code point, right? So that's the first thing that it does. And next code point, there has to be some place. Yeah, so it's basically like, okay, are there any more bytes left? Oh, there are no bytes left? Okay, I'm done here. And bytes.next is we should find out what it is, but it's also going to be something that is. So keep in mind that we're internally using an iterator of slices, which is also like in theory seems crazy that you would use it. Like you probably would not have done that in Ruby. Fn next. So this is basically like, I assume. I actually don't know what it does. I've never seen that before. It's intrinsic. Unsure what it does. But we make sure that the pointers are not null, and then it says, okay, if we're actually at the end, none. So next code point, I keep losing the thing I'm trying to say. But next code point basically calls bytes.next, which is going to basically end up saying, okay, it may even be that it's already, no, it's not going to be null. So it's basically going to say, okay, the pointers is not null, but we're at the end, so fine, we're done. And at the end is also a very small operation, right? So it's not surprising that the empty string is blank because we have a array of no bytes, and arrays of no bytes are very fast to discover that they're empty.
Mm-hmm. Do you have a comparison for what these the amount of nanoseconds it takes to do these in Ruby?
So we should actually go back and show how we integrate with Ruby. Mm-hmm. Unfortunately, I don't actually have the benchmark setup that me and Godfrey did, but surprisingly, or perhaps not surprisingly anymore, the benchmark that when we ran the benchmark against the C code, it was actually faster. The reason I can't say exactly why, but I think my hypothesis is that RBEnc endpoint len is basically a thing that's like, okay, I need to find out. So basically the way this code works is it says, you give me a string, I'm gonna make some stack allocated stuff, get the encoding out of the string, which is fast, get the pointer out of the string. Actually, he also has the fast path. So basically, like Rust is doing this fast path for you. If the string is empty, then you're done. Get the end of the string, keep looping while the current pointer is smaller than the string, and then what you do is you basically say, give me the size of the next code point for this string, and give me RBEnc code point len is confusing, but I think it's just give me the next code point for this string, and you're using the s pointer to move to say where the offset is, something like this, and then you get the code point, you loop through it. So this function over here is just not as good as the Rust function, basically, right? So in principle, this function could be generic, but one of the things that I noticed when I was looking at the Ruby code for this, so I was surprised that the Rust code was faster, because I was like, it is like competing with literally the thing that you could type if you could type it the fastest. So let's find the definition of RBEnc code point len. It looks like it's in this file. So it's basically like you get a couple of character pointers, you get length, and you get an encoding, and it's like it's basically getting a length. It's doing some checks, right? I think this is like the important function here, RBEnc precise. And it's basically asking the Oniguruma engine for the size of the code point. And I suspect, remember I showed you that code before that was like, the order of this is important for performance. I suspect that code is just better than, so the fact that it's like competitive, it's not like 5 times faster, means that the Ruby code is not embarrassing, right? The Ruby code is fine. Yeah. It's just that the Rust code, basically when you write Rust code, you get to write it fairly generically, and you kind of let the compiler figure out what you're actually trying to do. And so it's much harder to write good optimizations when you have to do everything by hand. It's much easier to write effectively a tree of functions that have the little pieces, generic functions that you compose in a way that ends up resulting in the correct optimization. One thing that's also different about this code is that this code in principle supports any encoding, not just UTF-8, although Rails doesn't care about that. So ActiveSupport doesn't need to care about it. And so there may be some cost related to, like, in Rust, we literally could just inline that whole thing that does the next code point thing. In Ruby, it has to be some kind of, okay, what encoding is it? Let me dispatch to that thing. You can imagine Ruby having a fast path for UTF-8, but it just doesn't. It doesn't at this level. It may have it deeper, but unlike in Rust, at some point, if you start doing dynamic things, the compiler loses the thread in C. So, okay, so it's very fast and seems good. I don't have benchmarks, but again, I can assert that we did benchmarks, and when we ran this in release mode, it was fast. Okay, so that's all basically how you write it in Rust. That was like a whistle-stop tour. However, I will remind you that the thing that we have been whistle-stop touring is a thing that is very simple to write. And a thing I also like about Rust is that even though there's a lot of optimizations going on, unlike something like LLVM, which is doing optimizations, and basically like Voodoo to understand it, you will not be able to. It's like plausible to understand the stuff that I just said. There's I hand waved over some stuff, and there's some type stuff you may not necessarily know, but the rough contours of what is happening is easy. And what that means is that you yourself, once you get to like intermediate or advanced level of Rust, can actually write efficient abstractions using regular programming tools that will still perform at the level of like hand-tuned optimized code, but where you would normally have needed Voodoo to do it. So, and Rust is just sort of giving you the right path for that. Yep. Okay, so here we are. We have a very simple function, and we have now, reminder, we have exposed it as a C function called tr stir is blank, and we would like to use it from C. So we are going to have a regular, seems okay. We are going to have a regular setup, and remember before I said there's init, so there's init turbo rails, defines a method on C string, so this just allows us to reopen the C string. We add blank question mark, and we say that it's RB stir blank, and RB stir blank, the template for a Ruby function, normal Ruby function, is that it's a function that returns a value, and a value is just the C representation of a Ruby object. It's whatever the name is. It has to take usually values because it's basically going to get those things from your Ruby code, so it takes other Ruby objects. And you also say when you define the method how many arguments it's expecting. And so if I took, in this case, probably be more idiomatic to have typed self here, honestly. If I wanted to pass an argument, some flag, then there would be like maybe value is foo or whatever, and then I would just change that to say 1 argument. Mm-hmm. Right. So it's pretty simple. I actually think the Ruby people did a pretty good job at the template for the C API. And then the next thing that we do is we're just going to call tr stir is blank. So we define tr stir is blank here. We're calling it from here. The only thing I had to do here was I just had to write a C prototype, and the C prototype is Booleans are in C, although I could have imported Boolean. So it's a function, it returns a Boolean, so it returns an int here, tr stir is blank, and then I return a buff, and what you can see here is that I have effectively, let me bring back, so this is actually a cool thing about Rust. So we hand waved a lot over the buff, but note that I made a buff. I said repr C, which basically means this should be represented in the same way C would represent it if I typed out the same thing in C, and I say it has a pointer, which is a pointer to bytes, and it has a length, which is the usize just means platform size, and that the reason you use usize with collections basically is that usize represents the maximum size of usize is the maximum size of memory on your system, hand wave roughly speaking. And if you said like U32 and you wanted to allocate a really big buffer that was 10 gigabytes large, you would not be able to. That's the old Windows problem, right? Everything was U32. So when you were talking about something that could be arbitrarily large as a collection, the idiomatic thing in Rust is to use usize to say this can get as big as the system allows it to get. And generally, there was a huge thread that I was part of about, it used to be that usize was the default, but that's actually really confusing when you're like trying to take numbers and now you don't actually know the size of the number. And if you're testing it on 64-bit and suddenly it does something different on 32, that's really confusing. But occasionally you really are just saying like, it's as big as the platform can give me memory, right? So we said pointer mut 8, we just make a void pointer here, same thing. Usize converts to size t over here. So we have basically taken this struct that we wrote here, like I said before, this marker is not a real field. It doesn't exist in the real world. It's just, it's basically in Rust, if you don't actually create a borrowed thing in Rust, you have to actually tell it what the lifetime of the thing is. And in this case, what we are saying is, what we're saying basically when we call, I guess what happens is we get this type from C, right? So we're basically saying like whenever you first see it, that's the right thing for it, right? So basically when we get a buff over here, we're basically saying it should be bounded to this stack, right? It's kind of like saying this, right? It's a function that has a lifetime attached to it, and that's the lifetime of the buffer.
Okay.
And basically the problem is that because we're not actually creating the buffer in Rust has no idea what the actual lifetime is, and so we're just saying that there's a marker in here that we can use. Okay, so again, we make the struct. This is pretty idiomatic. I wrote a function that just lets you convert a string into a buff, and it literally just gets, so Ruby has some APIs. This is like the hard part about learning Ruby C extensions, honestly. Like there's 20 or 30 macros that you have to learn that allow you to convert every possible Ruby type into every possible C type. And in this case, I have a string, I want to convert it, get a pointer out of it. I have a string, I want a length out of it. I do this, and I'm basically just populating the pointer that I got from Ruby into the slot over here. I'm populating the length I got from Ruby into the length over here. Basically, from Rust perspective, this code actually creates a new buff, right? It's the same. And actually, the nice thing about RepRC is that it's actually, like this thing over here, is that it's like takes such a load off of you. You can basically just type the thing in Rust, and note that in Rust, we're just totally using it like a Rust type, right? As far as Rust is concerned. In fact, we're just testing things with buffs that we made in Rust, and everything's great, right? And when we type buff wrap over here, in this case, there's a string that we actually got from Rust. So in this case, the lifetime of the buffer is the lifetime of the string that we got, right? That's what this thing means over here. And in the case of, but when we get it from C, then it's basically when we first see it. There must be some, there's some magic here that I don't know exactly what's happening. It's fascinating. Okay. Okay, so basically what happens is we have this thing, stir to buff is basically saying, okay, take the Ruby string, convert it into a buffer, which just does this code over here, right? And then we call trstir as blank. Trstir as blank takes a buffer. Again, that when we made the buffer over here, it's the same as making the buffer over here, so it just takes a buffer. Everything's great. And if this returns true, right? So this returns a Boolean, but it's basically an integer. If it's 1, it returns Q true, which is the Ruby internal representation of true. Otherwise, it returns Q false. And that's basically the whole story. And so what I kind of find interesting about the bridge here, first of all, it's not very big. There's definitely some voodoo, but whatever, you can learn it. And we should make it easy. My opinion is that this buffer thing is probably a thing that just should be part of the normal way that you write Ruby. Like you should not have had to write this macro. You should have gotten it from a library. You should not have had to write the buffer struct. You should have gotten it from a library, etc. But the nice thing about this, if you imagine that you did not have to actually type any of this code, right? So let's just like focusing in on this code here, is that you basically had a function that you wrote in Rust. You said that function was extern C, which means it's just a C function. You return a bool. We know what that type maps to in C. Awesome. It's an int. Great. Takes a buff. We have a mapping between, imagine that we were using a library. We have a mapping between those types. Everything's great. It's very easy to write it because it's just RepRC. And then we can just call that function with the thing that we got, and we're done. And one thing that I'll point out that was a part of my talk at RustCamp is that I actually think it's, there's basically 2 ways of modeling this kind of API. One way that you might model it is you might write no mangle pub extern c fn tr stir is blank, and then maybe instead of taking a buffer, maybe you take a b star mute, let's say ptr star mute u8 directly, and then you also take a len of usize. So you could write this and then return a bool, and if you wrote this code, you would then have to you would basically have to do all the work that's happening inside of this buffer abstraction, right, to unsafely convert it into the right thing. And the nice thing about using the buffer abstraction, in my opinion, is that it makes it really easy to, first of all, abstract the whole thing, which is good. But second of all, it makes it really obvious what the requirements of the C side are. So in this case, the requirements of the C side are, when you call trstir is blank, you are giving a buffer. A buffer has a lifetime. that means that from Rust perspective, it's not mutable, so we're not going to mutate it. I promise you we're not going to mutate it. I promise you we're not going to hang on to it because we just borrowed it from you. So that's what this tick A is doing for us. It's making sure that Rust knows that it can't hang on to it. So like I said before, it would not be good if you were allowed to say thread spawn B, right? Because basically the Ruby code is calling into us, and now it's like moving on with its life, right? You probably do not want to keep using it.
Yeah.
And if you just use star mute U8, you might forget to care about that, right? But here, the buffer abstraction has already encapsulated the invariant, so it makes sure that Rust does the right thing, but it also communicates over the boundary to the Ruby side some things about mutability, right? So, for example, one requirement is that the Ruby side is not allowed to mutate this string while this is happening. So you could in this case it doesn't really make sense because it's being called directly, but you could imagine that the Rust side has a callback and it calls back, and in that situation it would be important for Ruby to know that it's not allowed to mutate this thing. It would also be important for Ruby to know I have a list in my talk, you should watch it, but basically there's a set of invariants that you assume, and that when you write Ruby code you can make sure to enforce. And effectively what this is doing here, what this abstraction is doing for you, is it's saying the Ruby side can make some assumptions about what the Rust side is allowed to do, because we know that we're using a type that Rust understands, and the C side has some rules about what it's allowed to do, and it can enforce them. And I think that that's just way better than this thing, which is sort of the canonical, like basically once you have a mute of U8, look at what buffer has to do, right? So in order to get a slice, buffer has to write this unsafe code, right? So basically what would end up happening is you would just do this yourself, right? You would basically say like let slice equals, then you would say this, and then you would go in this particular branch, there's no, so you do this. Awesome, I have now unsafely converted to a slice, but now you as a person writing an FFI library has to actually remember how to do this correctly.
Yeah.
And this is actually much worse in my opinion. And this is also true even if for a simpler case where you were just like, if you just wrote pub extern c fn, like my example usually is skylight examples like get trace ID. So get trace ID might take a trace object and might return a number. So that's going to be like a U32. And basically what it's going to do is it's going to just return trace.id. So it has access to the private field. It's going to return it. Have a nice day. Seems good. Obviously, it's going to be a relatively fast function to call. And maybe like if you're worried and you want to catch exceptions, there's an RFC that I talked about earlier that I showed my giant comment about. Or did I? I did not. I will get back to that. But basically, there's an RFC about like being able to say that you can recover from exceptions, and you might want to have some kind of abstraction for communicating the exceptions and all that. That seems fine. But the point is that you would write this function. But if you wrote it in, I actually like the fact that you're taking a borrowed pointer, because it means that if you call like trace.getID, all the rules of Rust normally apply, right? Rust is not going to take that borrowed pointer and do some stuff and whatever, right? Whereas the more idiomatic way, actually it's not idiomatic, the more traditional way of writing this code would just be to say, I don't really know what's going on, I'll just take a star mute of trace, and then I'll transmute it or something like that into the thing, and actually dereferencing requires unsafe code, right? So basically at this point you have a thing that on the one hand people think is more honest because you're talking to C and C is unsafe. But my perspective is all the Rust type is saying is what the rules are for calling this function. And when Rust calls a Rust function, the rules are enforced by the compiler. But when C calls a Rust function, it's up to you in C. But that's fine, right? I think it's a lot, basically if you did some unsafe code in here, it's going to be a lot harder for the person who's writing this code to read this code and figure out what the rules are, right? But when you write it like this, it's like the rules are really simple. Yeah. The rules are the same thing as any other borrowed pointer in Rust, right? So I think, and this was what my talk at RustCamp was actually all about, was effectively writing FFIs where you use Rust types at the boundaries. Actually, I should for everybody's edification, I should actually run the code. I should probably not spawn. Actually, it probably would be useful to show the type error. Let's just use, I think it's like thread, but I'm not sure. We'll find out. Fascinating. Let me try to remember this API. I think it's just lowercase thread spawn. No. Okay, seems good. So if we go back and we run it's like, oh my God, what are you doing? You are a terrible person. Actually, interestingly, did I screw something up? Because so I feel like b.slice is actually not, interesting. I understand more what is happening now. But basically the point is that we have written a thing that actually prevents us from writing this crazy bad code, which seems good. Okay, so we're not going to write that code because it's not going to compile. Now let me actually just run, finish and actually run it in Ruby, and then I think we're done. Yeah. So first of all, you have to write an xconf.rb generally. Xconf.rb are voodoo, massively cargo-culted. Maybe someday someone will make something nicer. But basically what you end up doing is you have to populate some variables. So in this case, where can you find my libraries? And remember, cargo puts my libraries in this case. Let me run cargo build -- release. I'm not using thread anymore. I should probably remove it. So I actually really like, by the way, the fact that Rust has those kinds of warnings. Because it's basically like, hey, you're not actually using that variable. What are you doing? You usually turn them off for like a minute when you're writing code in the first place. But then once you have something that's stable, that's in production, every time you get one of those warnings, it's like something fishy is going on here. So we compiled the thing, right? And now if we go back, so I was going to do tree target. So basically you can see that the release thing has a thing called turbo rails in it inside of here. And that's the thing that we actually want to run. So we basically are going to say, okay, you can find a library of some kind inside of the target release directory. This is just how in Ruby we can walk up the path from the current physical file. Dir config is basically just a thing that you can do to say in xconf, the turbo rails configuration default is libdirs, but then you are able to say when you run xconf, you can say -- with turbo rails dir equals whatever, which maybe occasionally you have had to write at some point, and bundler actually lets you write it. So basically if somebody for some reason had the .a file somewhere else in their system, they would be able to do a bundle build .turbo rails and give it the other thing. Okay. Which actually you could imagine is useful, but it's like generally speaking not actually the right thing. And then finally we basically say, okay, when you actually compile it, you need to get the turbo rails library and then make a makefile, and this is like the magic line, which is basically like go make a giant makefile for this thing. And then what you do is you go into ext, you run ruby xconf.rb, makes a makefile. If you look at it, it's like actually a pretty big thing that Ruby has made for you. If you run make, you get a .so file, and you may not know this, but you can actually just require .so files if they were made in this form. So you can just require turbo rails. Now we have required it. You probably know that blank is not part of Ruby by default, but if you recall, we said that it should be. So when we required this SO, it's basically going to automatically run init_turbo rails. So it basically says like, you ask for turbo rails, I will run init_turbo rails, basically. And then now if I do like this .blank, it will work. If I do like this .blank, it works. If I do this .blank, it does not work, right? So that's it, it works. When you actually make a gem, so if you do this xconf, basically it will work. If you make a gem like this and actually deploy it, what will happen is that turborails.so will end up in a directory that can be required. It's either the lib directory or somewhere else on the load path, but basically if you just install this as a gem, you would actually be able to require turborails. And so now there's one last question, which is like, okay, I have a Rust compiler. Seems great. I can make that a file. And I think that works. That actually works great if you're like Intercom and you're like, oh, I just want to write some Rust in my thing. You can just make your build bot actually compile it. And I actually think that that's a pretty nice story for like apps. Just like have a Rust compiler in your environment, run it, everything's great. But Skylight, of course, does not run on your box. We have to give you a binary. And so we have to actually ship a some binary that actually runs on all machines. And the version of the binary that Cargo has spit out here is actually not totally general. It's for 64-bit Linux with a particular version of libc. Now the good news about libc is that libc is very compatible. So if you run on an old version of libc or compile an old version of libc, it will usually work on new versions. But if I compile on my whatever Linux I happen to have running here, it will not run on older machines, right? So there's a couple of things that you can do. What we actually do in Skylight is we build on CentOS 5.10, which is effectively the oldest Linux that anyone is really using. And that means that it compiles against a fairly old libc. And that means that the binaries that we produce for 32-bit and 64-bit Linux effectively run on every 32 and 64-bit Linux. And we just, in our XConf, we check your platform and then we download off of S3 the right ones. We don't want to have like many .a files. And we do the same thing for Darwin for OS X, right? So that's one strategy. It works out okay. Basically what we do is we still compile the C code natively using like the normal Ruby process, because of course all these macros that you're using, like this Ruby code that you're using may be different per Ruby version. And so we don't want to have to also figure out what Ruby version you're using and then ship a binary. Ruby is actually pretty good at compiling this code, right? Mm-hmm. So we compile the .a file, right? So if we go back to our tree, nope. So we compile this .a file once on the CentOS box, and that's the thing we put on S3, but and then we download it, and then we basically do this equivalent thing where we say like where it's located, but in our case, it's the place we downloaded it to, right? So that works fine. I think ultimately there's a better story coming, which is basically, first of all, general cross-compilation. So if you are a wizard, you can make cross-compilation work. I think Rust, as you have seen, one of the goals of Rust is to make things tractable for non-wizards. And so I hope that Cargo will eventually have a thing where you basically just say, I want to cross-compile to like 32-bit Linux. Please do that for me. And it will like download the toolchain, put it in the right place, etc. Give you spit out a binary. So that's one thing. There's also a thing called Muscle, which is a portable version of libc. Let me bring it up. Muscle. So so the way libc normally works is that whatever your kernel is, so libc is basically like all these interfaces, the way the user line talks to the kernel. So the kernel has a thing that's like read from a socket, and the exact way that you read from a socket, the exact system call might be different on different systems. So every system distributes with a version of libc that knows how to actually make the system call, the underlying system call. A big part of it, of course, is just extra libraries, like the code that actually buffers I/O doesn't need to be different, but enough of it is non-portable that you end up really wanting to use a version of libc that was designed for your platform. Like I said, Linux is pretty compatible going forward. And basically what Muscle does is it just makes one version of libc that works on all platforms. Okay. And because of that, you can statically link that. So normally you don't want to statically link. If I statically link the libc that's on my system and give it to you, there's a good chance that it will not work, right? It will explode because it's going to be talking to something that doesn't make sense for your kernel. And by a good chance, I mean it can happen, and when it happens, you will have basically no idea what's happening. You will not have a good enough mental model to understand it. Whereas with Muscle libc, you basically embed it once and it works. And there has been a big effort. It was like been a big priority for Rust to add Muscle support. So yeah, I think this is probably the best. Yeah. So basically, we have been moving towards actually just making it possible to say cargo build -- target of Muscle basically, right, and getting that. So that's also awesome. This is actually a thing that Go is good at, and I think it's a big reason for Go's success actually is everyone who has to build a CLI tool has the problem of like, how do I actually get this onto people's machines? and it's nice to be able to build one binary that works everywhere, like on all Linuxes basically, or at least all 32-bit Linuxes reliably. And Muscle basically lets you... what Go did is they effectively wrote Muscle inside of Go. And Rust was like, that seems like a big project, so we'll just use Muscle, it already exists. So that's happening. And there's also... I think there's various... I think ultimately what you want the story to be like the Go story, where you basically can make a binary and you're pretty sure that's going to work on machines. Right now, like I said, it took us a long time to really realize this fully when we worked on Skylight, but basically the most reliable story right now is to compile, if you're trying to target Linux, to just compile on a old CentOS box that is like as old as possible.
Yeah. What do you think the future looks like specifically for like Ruby or Rails developers?
So I think the thing that's cool about Rust for me with regard to Ruby developers is that I think actually writing, so like DHH said like years ago about Campfire, like, oh, Ruby is fine, but sometimes you need speed and then it's okay to drop down to C. And I think, first of all, everyone was like, cool story, bro, at the time. But I think it never really became a thing. And I think the reason it never really became a thing is that it's just too dangerous, right? Like, the reason Skylight ended up using Rust was that we considered using C++. Like, we actually... When you're collecting data from your users' machines, you have a very fixed budget for how much you can do, and we are very ambitious. We want to collect things like memory allocations, right? So we collect memory allocation information and tell you which endpoints are allocating a lot of memory. When we wanted to do that feature, it was simply impossible for us to do it without making the process of collecting data much cheaper. And there's just hard limits on how much cheap you can make it when you're writing it in Ruby. So we originally considered writing it in C++, but I think we were all pretty nervous about, like, we're asking users to run our agent in their machine. If it's seg faults, they're probably going to be pretty upset. And also, we can't get into their box to figure out what happened, right? So I think we were pretty nervous about C++. And so the reason we ended up writing in Rust was that we have like 5 developers of varying levels of skill. And we felt pretty confident that any developer could drop in and fix a bug in the Rust code. And as long as the resulting code compiled, they're not going to crash our users' machines. Which sounds... On the one hand, it sounds like obviously that is a requirement. On the other hand, there is literally no other way to do it, right? That is the only way that you could write code that when you compile it, you have a high probability, a guarantee that it doesn't cause seg faults on your user's machine. If you also have a requirement that it be reasonably fast, the only way to do that is Rust, right? So we got involved in Rust pretty early because we actually just had that requirement. And I think Rust is probably the way that DHH's original point is real, right? If you're not going to actually drop down and write some middleware in C because it's just too dangerous. First of all, almost nobody will know how to maintain it, but even people who do know how to maintain it can easily make mistakes. If somebody edits, especially one thing that I've noticed working on apps for many years is that the way people react to emergencies is not very good, right? So if there's a bug that someone feels like it's critical to fix, it's very easy to do sloppy things. And if you're doing sloppy things in a language that is not safe, it's very easy for those sloppy things to lead to seg faults, right? So, and I think that cycle causes people to be very scared of writing C code. And I think Rust has a good, plausible story. Now today, the actual embedding story, while it's not terrifying, a human can write this code. The actual C code that you write is pretty small. So this example is not doing a lot. The actual Skylight agent is large, is thousands of lines of Rust code, and there's just a few C entry points where you say things like, give me a handle to a new instrumenter, now make a new trace, now start a node, end a node, right? So there's basically a fixed communication, but the actual underlying code is very big, and it's still like the C wrapper still looks like this, right? It's just a bunch of functions that call into the Rust side. So actual embedding is not so hard, but I think that it's still a little too much voodoo, and I think probably before it becomes like really, really tractable for a lot of teams, some of the voodoo has to go away. But I also think that making the voodoo go away is like eminently tractable problem compared to actually making Rust in the first place, which is not a tractable problem for most humans, right? So a thing that's pretty common that people end up doing is there's the notion of like an IDL, which is basically a way that you describe more generically. So you might have a way of describing generically what the interface between C and Rust is, and then you might use that to effectively generate this. You sort of have part of it already. Like you can figure out, if with some rules, you can basically convert this into this line, but actually making this whole stuff requires a little more. So you can imagine having an IDL that's basically like class Ruby string, and then it's like reopens string, and then it's like I should probably use Ruby syntax if I'm trying to illustrate a Ruby point. Usually IDLs are not. And then you might have like def blank equals, have to be something like this, and then you basically say like, or maybe it's like a restricted syntax inside of the def. You say like, if you basically say, you probably need some type annotations, right? So so string is okay here, but you probably would need some way of saying what you expect the type to be, and then you say something like, what was it? Tr stir is blank, and then you can pass in self, and you could imagine that if you pass in a string to something and it's type annotated, it knows to do the stir to buff thing, right? And then maybe you say, you can say something like this, or maybe you have to be explicit and say true or false, right? But you could basically imagine some very, very restricted, this might look like Ruby, but it is not. A very, very restricted DSL that lets you say how you bind the Rust code into the Ruby code that just spits out this thing, right? Because it's so mechanical, the actual process of defining the binding should not be too bad.
Yeah. Cool.
Cool.
That was great. Thanks very much.
No problem.